Chemical reactions don't just rearrange matter, they also move energy. Some reactions feel hot and explosive, while others feel cold and sluggish. This simple observation hides one of the most important ideas in chemistry. Whenever bonds break and form, energy must be absorbed or released, and that energy flow determines whether a reaction can power the world or barely happen at all. This is the learning studio, where chemistry is explained through cause and consequence rather than memorized rules. And after understanding how chemical reactions transform matter, the next logical step is to understand the energy changes that make those transformations possible. Most people think energy in chemistry is just heat measured in experiments, but in reality, it explains why fuels burn, why food gives energy, and why some reactions require constant heating to continue. For example, when gasoline burns in an engine, energy is released that pushes pistons and moves vehicles. When ice packs feel cold, energy is absorbed from their surroundings. These opposite effects come from the same underlying principle: energy stored in chemical bonds. At the atomic level, the mechanism is precise. Breaking chemical bonds requires energy, while forming new bonds releases energy. If a reaction releases more energy while forming bonds than it absorbs while breaking bonds, the excess energy is released as heat. This is an exothermic reaction. If a reaction absorbs more energy than it releases, heat is taken in from the surroundings. This is an endothermic reaction. Every chemical reaction is essentially an energy accounting process. This understanding was formalized through the work of Germain Hess, who showed that the total energy change of a reaction depends only on the initial and final states, not on the path taken between them. This insight made it possible to calculate reaction energies without performing every experiment, turning energy analysis into a predictive tool rather than a trial and error process. As chemistry advanced, this concept became central to thermodynamics. Scientists learned that energy changes determine whether reactions are spontaneous, how much energy they can deliver, and how efficiently chemical processes can be scaled. This knowledge allows engineers to design fuels, batteries, industrial reactors, and even metabolic pathways by controlling energy flow at the molecular level. Once energy in chemistry is understood, the world becomes easier to explain. Power plants rely on exothermic reactions to generate electricity. Refrigeration depends on controlled endothermic processes. Living organisms survive because chemical reactions carefully manage energy to maintain order in a constantly changing environment. And once we understand why reactions release or absorb heat, the next question naturally follows. If energy controls whether reactions happen, then what determines how fast those reactions occur? That question takes us directly into the next episode, where we explore reaction rates and why some reactions happen instantly while others take years. The science of chemical kinetics.